colleague Krieger from Cambridge.
Indeed.
Going to give a survey talk on arithmetic dynamics.
All right. Thank you to the other organizers for having me give a talk. So yeah, I'm local. So if you weren't here yesterday, I'm a person who you can ask questions about Cambridge. My student Aisha is also such a person. So I encourage you to do so. So for the talk today, I don't want to assume anybody knows any number theory, which I hope is like getting enthusiastic nods from at least a couple of people. So, but what I want to do is present to you sort of the two main, like purely number theoretic tools that arithmetic dynamicists, algebraic dynamicists, and even complex dynamicists use to answer questions that require arithmetic. Okay, and so I'm going to do that via sort of two example theorems or conjectures. In fact, they're not fully answered. Questions which are not arithmetic in nature, okay, but which require arithmetic dynamics to answer. All right, so the first one is essentially the question of how many periodic points or pre-periodic points determine a rational map, okay? So let's assume I've got a map for me. I can't bring myself to write Riemann sphere. I just always write P1 over C. But my maps are rational. So every map in this talk will be algebraic, okay, defined by polynomials. And so what is a meaningful interpretation of this question? I mean, so of course, if you recall the period or the pre-period and the period of a lot of points of your map, that completely determines your map, right? And so really, we're asking this question in a set theoretic way, that if you hand me a set of points, which I know are pre-periodic for the map, to what extent does that pin down the map? And so here's the conjecture, which I'll explain sort of why we make this conjecture. This appears in a paper of Laura DeMarco, myself, and Heshiye, where we prove a case of this conjecture, which is that for all d greater than or equal to 2, there exists a constant, say b of d, depending on d, such that if two maps of degree d, do not have the same set of pre-periodic points, so for f and g of degree d, then in fact they have at most b common pre-periodic points. So the intersection of the pre-periodic loci is no larger than b of d, okay? And there's a couple of sort of pieces of content to this conjecture. I mean, the first thing is the statement that, and this is a theorem due to Matt Baker and Laura, there's lots of Bakers this month, by the way, Matt Baker and Laura DeMarco, that if the set of pre-periodic points don't coincide for two rational maps, then in fact their intersection is finite, okay? So that's a theorem. The assertion that we're making in the conjecture is that that finiteness is bounded in a uniform sense that depends only on degree, okay? The dependence on degree is definitely necessary, right? Just by interpolation, if I wanted to choose, 1 million points that two rational maps both had as common pre-periodic points, I could just make them fixed points of really large degree maps, right? And so then we would have that many points at least in common. So this bound has to depend on degree, okay? But this conjecture is not yet answered in full generality as stated. So I'll talk later about, when I give you the approach, I'll talk later about what's known. All right, so that's the first question. So again, not a priori arithmetic, at least not the question. The second one is perhaps more algebraic. And I will use a little bit of algebra geometric language here to say this the right way, but I'll tell you what you can think of if you don't like algebraic geometry. All right, so let me say this carefully and use the same notation I'm going to use later. So let's suppose that we have an algebraic dynamical system, okay? So in generality, what that would mean is a quasi-projective variety. If you don't like those words, you should think about just an n-dimensional complex space, okay? And a rational map. This is a map defined by polynomials, but possibly not defined on some locus where all of the points of x satisfy an additional algebraic relation. Okay, this is a Zariski open condition if you are happy with the language of algebraic geometry. If you don't want to think about that, and if you're thinking in this world, just think about f as being defined by polynomials or even rational maps. In the variables, okay? And let's suppose that we have what's known as an observable, or in algebraic geometric language, just another rational map, but now taking values in the Riemann sphere, okay, in the projective line. So and let's suppose that we have some kind of fundamentally simple algebraic object in which this map might take values. So suppose that we have gamma, which is a finitely generated multiplicative subgroup of C star, okay? And then the question is, how can orbits under the rational map F interact after application of pi with this finitely generated subgroup, okay? So properly stated, can we describe for some starting point x naught and x, the set of natural numbers such that the image of the nth iterate, I'm in a friendly crowd. I don't need a little circle. Okay. The image of the nth iterate of x naught, under F maps under pi into this finitely generated subgroup. Okay. So what you should think about here is like, you could be asking the question of, take like a map from P1 to P1, right? A rational map, and just take this to be the identity map, okay? And I could ask about how often the orbit of a point hits powers of 2, positive or negative powers of 2, right? Or positive or negative powers of 2 and 3, right? And the group generated by them, okay? So that's the kind of problem that you should think about. Indeed, in practice, this observable is usually just like a coordinate map, okay? That's the cases that we're usually interested in. All right. So notice that I haven't imposed a degree restriction here, by the way. So in the first question, the degree is at least 2. It's a chaotic map. But this even applies to linear maps, okay? And so there's no sort of hope of like a finiteness statement of the values n here, okay? Because you can think about the example, say, I'll work with a complex variable, z maps to z plus 1, right? And that powers of 2 finitely generated subgroup that I talked about earlier. And if you start with the integer point, 0 or 1 or whatever, you're going to hit this on sort of an exponentially defined index set in n, okay? Similarly, for a general P1 map, if I am talking about, say, degree D, and I take this to just be, say, the point set 1, right? Then I'm asking about hitting a point set with my orbit. Well, that only happens more than once if I'm periodic or pre-periodic, right? And so then I expect an arithmetic progression of indices to occur inside of this set. Okay. All right. So those are my 2 motivating questions. And the key point is that both of these questions are answered using Julia sets and escape rate functions. The problem is, it's somehow not enough to work with the classical complex Julia sets and escape rate functions to answer these questions. What we actually want to work with at the end of the day is an infinite collection of Julia sets and escape rate functions, and that's what we gain when we work in the arithmetic setting. So let me explain to you how that works. Are the questions both clear? Yeah.
Question.
Yeah.
For the first question, if the pre-periodic points of 2 functions are equal, do we have some relation between them?
Yes. So in the polynomial case, this is totally explicit. And it's basically what you would think, that they agree up to, say, an iterate and a symmetry of the Julia set. In the rational map case, there's also a mostly explicit relationship, but it's not quite as clean. Yeah. So, and I'm happy to give you some references on that later if you want. So yeah, it's a good point actually. We're saying, right, it can be the case that these sets are not equal, but the Julia sets have infinite overlap, right? And so really there's something non-complex that's being seen here, right? It's not just saying that the complex Julia sets only intersect finitely. That's not the case, okay? As we know from like interval examples, right? Okay. All right, great. So what are our tools here? Well, let me give you the basics. So the situation being arithmetic simply means that I'm working in a finite extension of the rational numbers. So a number field is any finite extension of the rational numbers, finite field extension. All elements of a number field are algebraic, meaning that they satisfy some polynomial relation over Q, right? So i.e. roots of a polynomial with Q coefficients. And the key thing here is that Q itself, as well as any number field, admits not just the classical Archimedean absolute value that we're used to from viewing Q inside of the complex plane and taking modulus, if you want to think about it in a complex way, but also has a full collection of p-adic absolute values for every prime p, okay? So in greater generality, the absolute values on K are, well, they come in two forms. One is the so-called Archimedean absolute values, and this is what we're used to. And this comes from any choice of embedding of your number field into the complex numbers, okay? This is the same thing as saying, if you are algebraically happy with this statement, it's just the usual modulus, so evaluated at the Galois image of a point. Okay, so for each element of the Galois group, we get an absolute value, and that's almost true, but they can be equivalent if they're complex conjugates. Okay, so the point here is that somehow if I take, say, okay, like Q root 2 is a finite extension of Q, but there's two embeddings. I could send root 2 to root 2, or I could send root 2 to minus root 2. And those are both perfectly good embeddings of this field into C. Okay, and they give me different absolute values. Okay. All right, but these behave in sort of the way that we expect them to. They really, studying these absolute values dynamically all comes down to complex dynamics, these Archimedean ones. However, we also obtain non-Archimedean absolute values. I will describe this just for Q, okay? I just don't want to have to talk about ideals and stuff like that, but it's not hard to define for a more general number field. So if P is a prime, and say A over B is in lowest terms in Q, define mu P of A over B to be the power of P, so the exponent rather, in A over B, that is, A over B is equal to P mu P A over B times, say, U over V, where P does not divide U and P does not divide V. Okay, so I pull out all the powers of P from my rational number rather. The exponent that appears here, which is positive if P divides A and negative if P divides B, is this value mu of P. Okay? Then the so-called p-adic absolute value can be defined to be P to the minus mu P of A over B. Okay? So this is how we define the p-adic absolute value. Trying to complete various spaces with respect to this absolute value gives p-adic, either integers or numbers if you like, depending on whether you started with Z or Q. The point here is that these are still absolute values. In fact, they satisfy an even stronger triangle inequality in that the absolute value of a sum is no larger than the maximum of the absolute value of the two constituents. Okay? All right. So the key property here, and you'll see the power of this statement when I talk about the proof of question 1, or approaches to question 1, is what's called the product formula. Which is that we have this infinite collection of absolute values on our field, okay, Q as I've written it, or there's generalizations to a number field K, but they are not all independent, okay? That is to say that for any non-zero element of the number field, the product, I call that X. Let me explain my notation here. The product of all of the absolute values with respect to, okay, say, yeah, sorry, I should have written notation first. This is the set of absolute values up to equivalence. So if my number field is Q itself, then this is just the usual absolute value together with 1 for each prime number, okay? This is the set of absolute values on K. This number is a normalization so that I don't care which number field I'm looking at X in, because I could extend this to some L and still make all of these definitions and hope for the same formula to hold. In order to make that happen, you take your absolute value, you complete it, complete the number field with respect to that absolute value, complete Q with respect to the absolute value, which restricts to an absolute value on Q. And you look at the degree of this extension compared to the total degree of the extension, which is finite by definition. Okay? And the product of all of these things is equal to 1. And the key point here is that one of the implications of this is that two numbers in a number field cannot be close with respect to all absolute values at once. Right? So thinking back to Alex's comment here, right? As I will make precise later, having lots of common pre-periodic points should mean that Julia sets are somehow close together, right? For the two rational maps. Okay. That's true maybe in the complex topology here. If we can sort of push the analogy through p-adically, then the product formula obstructs that being true for all possible Julia sets at once. Okay, so that's the goal for me to tell you enough about that for that sentence to make sense in the next few minutes. Okay. All right, so that's the basic algebraic number theoretic stuff we need. So the good news is that we do sort of, I mean, we're used to thinking of Julia sets and there's a sort of slew of equivalent definitions, right? We have topological definitions, we have equicontinuity or normality definitions via Montel's theorem, and we have definitions as like the closure of the repelling periodic locus and so on, right? And so you want to say like, okay, I can put some meaningful topology on this number field with respect to this p-adic or v-adic absolute value, and then sort of promote all of these definitions to define a Julia set p-adically. Okay, so indeed, let me write it this way. Our number field together with any absolute value that we choose, so for all, any absolute value, remember this was the collection of absolute values, we do have an isometric embedding of our field with this absolute value into a field which is algebraically closed and complete. Okay, and the topology coming from the v-adic topology, the induced topology from this absolute value. Okay, so that's the good news, right? Because if we're talking about periodic points, we definitely need algebraic extensions, right, to find roots of polynomials. And if we're talking about closed sets, we definitely want to work somewhere that's complete. The bad news is that this is topologically very bad. It's totally disconnected, okay, so everything is closed. And so what do we do to get around that? Well, I'm not going to tell you in depth because it takes like its own lecture. But there is a way around this to make sensible definitions of Julia sets, a sensible non-Archimedean Montel's theorem, and so on. And that is by enlarging the space CP and weakening the topology by embedding it in what's known as the Berkovich projective line. Okay, so I'm not even going to write anything. Just know that there is a solution to this issue of what is a Julia set p-adically. Okay, I'm going to dodge that for this talk by working with escape rate functions. Okay, because escape rate functions only need absolute values, right? So recall in the complex setting, if f is a rational map of degree d greater than or equal to 2, let's say we write f as f1 over f2. Let me not do that. Let me use that for the homogeneous. And say f equals f1, f2, some homogeneous lift of f to a2, which is to say that I wrote f as, say, g over h, and then took these two polynomials and homogenized them. Okay, that's my f1 and f2. So that I get two polynomials of degree d in two variables, homogeneous, which provides a map from a2 to a2. Sorry, c2 to c2, no reason for the a's. Then the homogeneous escape rate associated to this lift is, say, g sub f of xy, which is the limit as n approaches infinity of, what do I want to say here? I've got my f. Did I take max? Yeah. What did I write the degree? Yeah, I did. Okay, sorry. Of 1 over d to the n log fn of xy, where this norm can be any norm that you like on this finite dimensional vector space, right? So might as well take max of coordinates or something like that. Okay. All right. So this definition we're familiar with. So this is, say, max of x chord, y chord. I don't want to give the coordinates themselves names. Okay. The point is that this definition genuinely only uses the absolute value to define the escape rate function, right? And the fact that it converges only comes down to the triangle inequality. And so there's absolutely no reason why we can't say, well, actually, oh, I already got my red. Why not take a place? I didn't leave myself space here. Say I've got some place of a number field, assume that f is has its coefficients in a number field, okay? And then I can take the v-adic escape rate with respect to this absolute value v that I've chosen simply by putting little v's on my absolute value. Those are v's, not y's. Okay? So I get this infinite collection of escape rate functions, right? And anytime I take a point here, so now notice that in order for this to make sense, this will only be defined when x and y have coordinates in k, okay? Or actually, these absolute values always extend up to the algebraic closure. Well, as you can sort of tell here. So it's okay for them to live in the algebraic closure of k, which is the set of algebraic numbers itself. So as long as I take points with algebraic coordinates, right, then in fact I have a well-defined value of this lifted homogeneous escape rate function v-adically. Okay. All right. So let me make some comments on properties then. Almost everything you want is still true, with one caveat. So first of all, notice that it is still the case just by definition that for this lift f, if I want to apply log to the image of a point, v-adically, this is still going to be within a bounded constant of d times the log of the norm of the point, okay? This notation, by the way, means that the difference of these two things have absolute value bounded by a constant independent of p, okay? And it's also the case by definition here. Sorry, let me add a little v to my g. It's also the case that g transforms exactly with respect to f, which is to say that gf v of xy, sorry, let me put it this way, of f of p is equal to d times gf v of a point p, okay, by the limiting construction. We made some choices. So we started with a rational map. When we evaluate the escape rate of a point, we actually take two lifts, right? We lift the map. We could have multiplied both of these by a constant to get a different lift, right? And we lift the point. And again, we could have multiplied by a constant to get a different lift of the point. And so how does the escape rate transform under those two lifts? It's exactly the same as in the complex setting. So GFV of CP is GFV of P plus log of CV. And G, say CF. So if I modified my lift by multiplying both terms by a constant of P, then this is the same thing as the unmodified escape rate function plus log CV over d minus 1. Okay. And finally, I want to note, this is not just about this escape rate, this is a fundamental difference between somehow non-Archimedean dynamics and Archimedean dynamics. Even though this is an infinite set of absolute values, for all but finitely many of them, the dynamics are actually non-expanding v-adically, okay? And one can in fact show that for all but finitely many, this escape rate function, now let's put it this way, P, is in fact log of norm of P on the nose. Okay, this case is known as good reduction for the absolute value V. Okay. Yeah. In the last formula here. Log, yeah. Oh yeah, sorry, I'm like, there's no G. Yeah. OG. Good. All right, any other questions? I know we're going a bit quickly. No? All right. So the point is that the machinery of the escape rate function goes through. That's the point. And in fact, it's even better than that, right? So thanks to the product formula, we can make the following definition, the product formula and this final comment. So I know this is definitely not a survey talk, but I thought it would somehow be more useful to prepare you guys for a couple of the mini courses next week. So hopefully, well, I'm surveying a couple of results, but all right. So what is the point here? The point is that even though we've done this for one absolute value at a time, okay, the product formula tells me that there must be some sense in which these things glue together meaningfully, okay? And so we make the following definition, and I want to say it slightly carefully. So, okay, a number field. F a rational map with coefficients in K. of degree d at least 2. Then the canonical height associated to f is a function usually denoted by, say, like h hat of f. I'll write it this way. From the algebraic points of the Riemann sphere, so that's all the algebraic numbers plus infinity. Defined by the canonical height of P is the sum over all places in K, that's the defining number field of my rational map, of, again, I need a normalization here, just like in the product formula. And this is for any choice of lift. Let's say it this way, choice of lifts f of f and p tilde of p. Okay. So in practice, of course, you could just like take p comma 1 pretty much all the time, unless you're dealing with infinity. If you want to know the canonical height of infinity, you'll have to do something else. But the point here is that this is well defined, right? First of all, for all but finitely many places, there's in fact no contribution to this sum. Okay? Second of all, right? Imagine that p had integer coefficients, right? To say that in fact this has a v-adic absolute value which is different than 1 means that that prime that you're taking the v-adic absolute value for appears in the denominator of one of the coefficients, right? Sorry, I guess I said integer, rational coefficients, right? That only happens for finitely many primes, right? So whatever your coordinates are, right, this will take a value other than 1 at only finitely many places. And so this Green's function, this escape rate function, is 0 away from finitely many places. The second thing is that this is totally independent of either choice of lift. And the reason why is the product formula, right? So the terms I pick up if I change the lift, when I sum over the normalization, that's just log of the product formula, right? And the product formula told me that the product over all places was 1, and so the log of it is 0. So it's independent of choice of lift for either the map or the point. So this is a nice, well-defined function. And it inherits dynamically substantial properties from those of the local escape rate functions. Okay, so key properties. All right, so the first is that the transformation property that we might hope for. So if we apply f to a point, then the canonical height multiplies by d, the degree of the map. The second one is that this canonical height is always non-negative. Okay. That's maybe not, it's not quite free, except for the fact that you could always choose a lift of your point so that the absolute values are greater than or equal to 1, right? The third point is that this canonical height is within a bounded constant of what's known as the naive height, which is simply what you get if you use these basic log functions. Okay, so this is the height, which is defined to be the sum okay. This is both Archimedean and non-Archimedean places we sum over here, right? This, by the way, in fact, is the dynamical height function, is the canonical height function associated to the powering map, z to the d, okay? But so the value of the canonical height and the value of this so-called naive height, they always differ in absolute value by some constant, again, independent of p, this notation is telling me. And this leads us to the key point, at least you'll recognize from question 1, which is that the canonical height of a point is 0 if and only if that point is pre-periodic. Okay. So this direction is clear, right? So if we have a pre-periodic point, it's got to be algebraic, right? Because it satisfies a polynomial relationship with an iterative f. And the coefficients of f live in a number field, which are themselves are algebraic. So it's an algebraic point, so it makes sense to talk about the canonical height at that point. But of course, by definition here, I mean, the escape rate function is coming from a limiting process, right? And so if I've got a point which is periodic or pre-periodic, either way, then in fact, the growth of the escape rate function will not be exponential and will take the value 0 at all places. Okay? All right. The other direction requires a theorem of substance, okay, but I will tell you with words. So the thing is, if I have a point with canonical height 0, then all of its iterates have canonical height 0 too, by this transformation property. That means all of its iterates have a constant upper bound on the height, right? So there's some uniform constant for which all elements of the orbit of the point have height no larger than that, and by which I mean naive height, okay? But it's a theorem due to Northcott that in any single number field, you have only finitely many points of bounded height, okay? So the input here is what's known as Northcott's theorem, which says that any number field has only finitely many points less than or equal to some constant bound. Okay? And so the orbit of P then lives in a finite set, so P is pre-periodic. All right. Yeah, Julia. Absolutely. Yeah, absolutely. So just to sort of put you in the world a little bit, like if it's z squared plus c, this is something like log of c, like log of modulus of c. I guess it would be, since I'm taking the global object, this would be like height of c, actually. Yeah. Okay. All right, and one more thing that I should say, because it's the way that people usually introduce the height. I want it on the same board, so I'm going to sort of do bad board work here. 5, which is that with this tool of the naive height, there's somehow like a more general or more basic way to write this, which is that the canonical height of a point is nothing more than the limit, this is really bad board work, sorry, of the height of the iterates of the point properly scaled. Okay? So if I look at the height of the iterates, they should be growing like d to the n, okay? And taking that scaling into account, this limit always exists, and it is equal to the canonical height. The reason I didn't present it this way to you is that the power really comes from the local decomposition here when you're working in the arithmetic setting. Okay, that's where you do the real work. This formula, while very clean, and maybe helps you understand this even better, right, is somehow not as useful. Okay? All right. So let's go back to our questions then. I have 10 minutes each. Sorry, let's go back to your questions. Any questions? Yes.
Periodic, will it be escaped for some?
That's right. So if P is not pre-periodic, there must be some absolute value for which it's escaping. That's right. Because if not, all of the local escape rates would be 0. So that's a really nice point actually to make, because somehow, even though you could prove 4 with this formula, what you've just said is a much more meaningful statement, right? Having escaping dynamics is something we can actually use. All right, good. And it's worth saying also, I mean, okay, I can't tell you all of arithmetic dynamics in 1 hour, but of course, like a major field of study, an open question is, how small can this number be if it's not 0, right? If you have a point that's not pre-periodic, what kind of lower bound can you get on its canonical height? Okay, that's known as the dynamical Lamer question. All right. Okay, and now I feel like, okay, I'm going to go on a tangent here, but I want to say that if that question sounds interesting to you, there is a very beautiful paper of Philip Habegger and Harry Schmidt dealing with the dynamical Lamer question. And it's in a very limited setting, but it's very beautiful because it very much mimics Wessel and Dimitrov's proof of the Schinzel-Zassenhaus conjecture, which is a purely number theoretic thing. And it's potential theoretic and very nice. All right. All right, so let's go to the first question about common preperiodic points for maps which do not share the complete same preperiodic locus, which, yes, indeed does impose relations between the maps, although in the non-polynomial case, they're slightly messy to write down. So question 1. So each of these questions has a main arithmetic tool that I can now describe to you with the language of height functions, okay? And question 1 is actually sort of the more unpleasant one to write down, so bear with me for a moment. So this is a case of a very broad class of theorems known as arithmetic equidistribution theorems, about which I am sure you will hear quite a bit more from Mirto Mavraki, and I think Han Peters is also going to talk about some transcendental generalizations of these things. Okay? So let me give you a case of an arithmetic equidistribution theorem that we can get our hands on. Okay? So first, let me give a little notation. So given, say, an algebraic number x, what do I want to say here? So suppose F is a rational map of degree D, at least 2, with coefficients in a number field, so defined over a number field K, as before. Let X be an algebraic number. That is, it satisfies some polynomial with coefficients in Q. Okay, but that implies it satisfies some polynomial with coefficients in K, and we can choose the minimal such in terms of degree. So the Galois orbit of X over K is the set of roots of the minimal polynomial in K of X, KT satisfied by X. Okay. So again, if you're sort of algebraically happy with the Galois theory of algebraic number fields, this is just hitting the X with the absolute Galois group. Okay, so the Galois orbit of X. But you can also think of it as, okay, I've got an algebraic number, it satisfies some polynomial with coefficients in K, because it satisfies some polynomial with coefficients, it's the root of, rather, some polynomial with coefficients in Q, and so therefore some polynomial with coefficients in K, since Q is a subfield of K, right? But I can possibly factor that polynomial until I get the minimal one, which has, up to a constant, which has X as a root. All right. Then the arithmetic equidistribution theorem says the following. So suppose that I have an infinite sequence. Again, these are, let's say it this way, is a sequence of distinct algebraic numbers which have the property that their canonical height goes to 0 as n goes to infinity. Okay? This is what people refer to as small in this setting. So small points, meaning that it's a sequence. I don't want them to all be like the same periodic number, which is why I've imposed distinctness with canonical heights going to 0. So what should you think of? Well, by the transformation rule, this could be, say, the set of preimages of some particular point, right? When I take a preimage, right, then my canonical height is multiplied by 1 over d, right? We move it over to the other side if we're taking a preimage here. And so if I take successive preimages of a single point, then the canonical heights of those successive preimages will go to 0, right? So preimages of a single point, or any set of preperiodic points. Okay, so that's what you should have in your head. Then, the Galois orbit, I guess I didn't give this notation, let's say Gn of the xn, Galois orbits, equidistribute to a natural measure, to a canonical measure. So, which is to say that if I take 1 over the size of the orbit and then weight with delta masses every element of the orbit, that they converge in the weak star topology to some measure mu of fv viatically. And this is for each prime, or for each absolute value v on the number field k. Let me pull this up. Sorry, it's hard to see. Uh-oh. Okay. I think I've written down everything correctly here. So, okay, let's think in the complex world, right? We know what preimages equidistribute to, right? If you take a point which is non-exceptional for your rational map, meaning it has an infinite set of preimages, and you start looking at exactly the measure, which is delta mass supported on this collection of preimages, and pull back, pull back, pull back, pull back, the limiting measure is the measure of maximal entropy on the Julia set, right? And so we can also write this, since I've been doing, sorry, I just cannot reach the top board. I've been doing this all in the language of escape rate functions. So perhaps the nice sort of way to write this is, say, this way, okay, that this is a distributional Laplacian of the escape rate function, the local escape rate function, since this is also true in the complex setting. I haven't told you what this means in the viatic setting. Don't worry about it. Okay, it's easier if that helps. But so the point is that this is the usual measure of maximal entropy. So totally invariant measure of maximal entropy. For V Archimedean. And kind of a mess if V is non-Archimedean. So it might not even be supported on CP. If V is non-Archimedean. Okay, so again, I can't really get into it in so much depth without talking about the Berkovich projective line, which I don't want to do. But the point is that if I have a sequence of small points, right, so including these particular examples that we're used to, then in fact, the geometry of those points for any choice of topology relevant to this number field, right, so for any viatic norm, the geometry of the points is constrained by the support of a natural measure, right? So in the Archimedean setting, this is saying, say, for example, if I have 2 rational maps and they have loads of preperiodic points in common, right? The same will be true for the Galois orbits of those preperiodic points. And that means that the 2 measures of maximal entropy must be almost the same. Okay? And this is indeed one approach to that question 1. Yeah, please.
So why was
It doesn't. It doesn't, actually. I mean, so the V comes into play in the notion of convergence, of course, because I'm saying that they're v-adically close, like the integrals that I'm evaluating the weak star convergence at. I'm taking like the integrals are happening over these Berkovich lines that I haven't told you about. So it's sort of embedded into the notation of the weak star convergence, and also the place where these measures live depends on V, so changes as V changes. But there's no like V assumption on the points themselves, I think is what I want to point out in answer to your question. Okay. What's that? It's hidden in the weak star and also in this notation, right? So mu of FV, this measure, this v-adic measure of maximal entropy, which it is indeed, a v-adic measure of maximal entropy, not only is it sort of living on this larger space that I haven't told you about, it might have support that doesn't intersect your number field or the algebraic numbers at all. In fact, that's the usual case. That good reduction case where I told you that the escape rate function is just the log, right? Then this measure is supported on a point of that larger space, which is not one of these sort of classical points, okay? It's not an algebraic number. It's a point which corresponds to the unit disk in the p-adic unit disk, okay? All right. Other questions? Okay, so big hammer, and this is not even close to the most general and high-tech version of this equidistribution theorem that's in place. I should make some attributions here, sorry. So the various versions of this equidistribution theorem were due to a lot of people. I should mention Touillet and Chamberlain and Yuan and Zhang and Baker and Rumley, and probably that's enough names that no one will be angry at me if they watch this. Okay, all right. So let's discuss then. I've pretty much verbally outlined the approach to question 1. Let me just write one sentence and then move on to question 2 because I'm running out of time. All right. So then approach to question 1, and this was the approach that my co-authors and I took. It's not exactly the approach of DeMarco Mavraki and other people who have made progress on this question, though all approaches on this question go through an equidistribution of this kind. But the approach is, if these are large, then mu FB and mu FG are very close at every place. And this can be made quantitative by a theorem of Charles Favre and Juan Rivera-Letelier, and using a particular sort of sum of energy pairings at each place, which really measures for you the proximity of these two measures. Okay, so you can cook up a number which is small if and only if the two measures are almost the same, or if you prefer to think of it in the Archimedean setting, the two Julia sets are really close together. Okay, and given this then, so in, for example, a one-parameter family, so if F and G are in a one-parameter family of rational maps, this implies that the two parameters that give us F and G, say F is, H of T1 and G is H of T2, if you like, that T1 minus T2 is small for all V. So for every absolute value, those two parameters must be close. Okay, this is a little bit of a lot going on under the surface here. But of course, the product formula obstructs this, right? So contradicting the product formula. of degree D defined over a number field. As long as they have algebraic coefficients, you can always choose a large enough number field to have both of them defined over that. Yeah. Contradicting the product formula. Okay. And this is the situation. So the cases that I did with my co-authors were one parameter family cases. We did quadratic polynomials and lattice maps of a certain type, Legendre. Mavraki-Schmidt completed the one parameter family setting, though not in quite the same way that we did. And the interesting thing about this is that one of the outputs of this procedure is a kind of, not a product formula per se, but like a repulsion formula for Julia sets, or if you prefer measures, right? That for two rational maps, the measures of maximal entropy, unless they coincide at all places, unless the two pre-periodic sets are the same, somehow they cannot be too similar at all places. So you detect a dynamical difference somewhere when you're in the arithmetic setting. And before I move to question 2, I'll comment that, okay, all of this is pretending that the rational maps have algebraic coefficients. Why can I do that? There's actually a relatively straightforward specialization argument, okay, which I won't outline. But reducing to the algebraic case from the complex case in this setting is actually pretty easy. All right. So with my remaining 2 minutes, and then Jasmine told me I could go over, so sorry, guys. 2 plus epsilon. Let me give you the main arithmetic theorem. So the takeaway I want you to have from this talk is these 2 arithmetic theorems, okay, in your toolkit. Okay, I'm about to tell you the second one, because everything in arithmetic dynamics comes down to these 2 arithmetic theorems. Equidistribution, or what I'm about to write down, which is Schmidt subspace theorem. Okay, so the arithmetic theorem here is known as the Schmidt subspace theorem. It's due to Schmidt from the 70s. And it is a theorem about how well algebraic numbers can approximate other algebraic numbers, okay? But I will not write it in that form. I will write it in a slightly more basic form here. So let's let, say, L1 through Ln be linearly independent linear forms in n variables. And let's assume that they have coefficients in a number field K. All right. This down, sorry. Then for every epsilon greater than 0, the set of integer vectors, yeah, I'll write it this way. Integer vectors, not all 0 coordinates, such that L1 of x up to Ln of x, this product has absolute value, or modulus, if you like, since I'm in a number field, less than or equal to the norm of the integer vector to the minus epsilon. So this set is contained in a finite union of proper linear subspaces of Qn. Okay, so, all right, what am I telling you? Let me give you a special case which you might have heard, which is Roth's theorem. Actually, probably everybody meets Roth's theorem in one-dimensional dynamics when we talk about like Siegel disks and approximation of birational numbers. Maybe not. But let me tell you Roth's theorem, since it's one of the more useful special cases of Schmidt subspace. So for example, if I take n equals 2, I take my first linear form, say in x and y, just to be y, and I take my second linear form to be, say, alpha y minus x, where alpha is some algebraic number, so that I satisfy the conditions of the Schmidt subspace theorem. Then this says for all x, or sorry, the set of, say, xy in Z2 minus the origin, such that the product of y and alpha y minus x is less than 1 over norm of xy to the epsilon. So for all epsilon greater than 0, is in a finite union of, well, linear subspaces which are proper inside of the two-dimensional space are lines. Okay. But if I think of xy as the lift of a rational number, right? So i.e., the set of rational numbers, say p over q, such that alpha is well approximated by p over q in the following sense, is finite. Okay, so what is the translation here? I'm taking a rational number, p over q. I lift it to pq here, right? Satisfying this inequality turns out to be almost up to a constant, equivalent to satisfying this inequality. Because if I'm close to alpha, then the difference between the absolute value of p and the absolute value of q is bounded, and so this height is comparable to either absolute value of p or absolute value of q. Okay, so just imagine in your head you're replacing this with absolute value of q, maybe say that's the larger of them, and then I've just divided both sides of this inequality by y squared, or q squared down here. Okay, so this is Ross' theorem. So this is about the quality of approximation of this algebraic number alpha by rational numbers p over q. And the finite union of lines here, of course, I mean, it's a union of lines through 0, sorry, I should say, through 0, since a linear subspace. That gives me exactly finitely many rational numbers down here. Okay, and I'm well over time, so let me just say a word. So question 2 was about how orbits intersect finitely generated subgroups. Okay, the point is that Schmidt subspace theorem doesn't just hold for the usual absolute value. Schmidt subspace theorem also has versions where you use this for v-adic or p-adic absolute values. Okay, and in fact, you can put lots of them together at once and get very strong Diophantine approximation statements known as S-unit theorems. And so the answer to question 2, the best known answer, which is due to Jason Bell and his co-authors Chen and Hossein, is that the way an orbit can intersect a finitely generated subgroup is in a finite union of arithmetic progressions for the indices plus a set of density 0 with some kind of natural notion of density, Banach density, if you're familiar. Okay, so think about that example I told you earlier. If we just take like the z plus 1 map and powers of 2, right? The indices of that map, which hit the finitely generated subgroup, are exactly, I guess, powers of 2 minus 1 or whatever, if you start with the starting point 1. So it's an exponentially growing set of indices. That's a very thin set of integers. Okay, and their result is that, okay, maybe you have some arithmetic progressions in there, which can happen, just as we talked about in the periodic point case. But once you throw all those arithmetic progressions away, what you're left with is a very thin set of your orbit hitting the finitely generated subgroup. And it goes through this machinery and its generalizations and a lot of other things. So, okay, with apologies for the extra 6 minutes, I'll stop there. Yes, sorry. Yeah.
So in the end of question 2, part 1, You said that it's easy to deduce from the general case, like for generic, general rational function to one which is the statement up there is for rational functions over finite.
That's right. That's right.
What about if I do general?
So the point is that somehow if there's any pair which has more than like b plus 1, you produce some bound b for algebraic ones, right? But then the point is that if there's any pair with non-algebraic coefficients, which realizes more preperiodic points, that's really like a function field statement because your coefficients are transcendental, and I can't tell the difference between like the transcendental pi and the transcendental e in the algebraic setting. And so the point is that if you produce this bound B for algebraic pairs, and then you have some non-algebraic pair F and G, which have B plus 1 common preperiodic points, there must exist actually an algebraic specialization where instead of taking pi, you say, oops, I meant pi to be actually square root of 2 that produces B plus 1 common preperiodic points. So from the algebraic perspective, there's no difference between the complex number pi and the transcendental number like t, like variable t. And so anytime you violate this, once you have the algebraic bound, violating it for a transcendental pair implies that you have a violation for an algebraic pair. Yeah. So it's really a function field argument. Yeah, Aisha.
So in the like arithmetic distribution results, you have like average over the Galois orders, and you put the direct delta constant on each of those. So if you like weight them differently, then do you get convergence to something that's obviously not the measurable Maxwell entropy but has its own like interest?
You might. So certainly you could make a soft statement and say I'm living in a compact set, like there's some subsequential limits. What can I say about the set of subsequential limits? I mean, maybe let me go to this side for 1 second before I answer more. I mean, we think of the example in the complex setting of like the powering map, right? The preperiodic points are the roots of unity. You can't just take like some roots of unity and get equidistribution to Lebesgue on the circle, right? You could always take the root of unity closest to 1, for example, and that would definitely not give you distribution to Lebesgue on the circle. So for example, that would correspond to giving everything a weight 0, except for one of the roots of unity. And so from that perspective, if you allow your weights to really vary freely between 0 and 1, you can get basically any measure that you want. Just talking about this z-squared case, supported on the unit circle, right? But I am sure that there are particular weightings that would be more dynamically meaningful, for which there would be some interesting answer to your question. But I don't think they're covered by any of the equidistribution theory. And the reason why is that, well, so behind all of this, really this measure is a curvature form arising from a metrized line bundle that's living on top of our space. And so one could imagine like maybe weighting the line bundle itself, and then you would get a natural curvature form associated to that, and maybe that would somehow see weightings on the points, but I don't know about that. Yeah, it's a good question. I saw another hand somewhere. Yeah, Julia.
Yeah, so like energy pairing. So can you get like an integral that relates like u of v and sine of 0?
Yeah, absolutely. I mean, like if you're in the polynomial setting, for example, this would just be integrating one of the escape rate functions against the other one's measure of maximal entropy, right? And so this energy pairing, sorry, locally, and so then summing up that integral over all places. Yeah, so yeah, happy to. So like idea of the energy. You can think of it in a couple of ways. So this is roughly, yeah. So like in the polynomial setting, this could be something like integrating, I'll sort of write the small Green's function. So I've taken my lift, but then I've pushed it back down. It's the polynomial setting, so I have like a well-defined escape rate anyways. GF F1 of Z, or sorry, F of Z against mu G of Z. This would be the local contribution to the escape rate. And so, so at each place. So GFB, mu G, B. Sorry, I know I'm overloading the letter G here. But so what you want to imagine, so let's think in the complex setting. Why is this energy pairing telling me how close the two measures are? I mean, the escape rate function for F is small when you're close to the Julia set of F. The measured for G is supported when you're on the Julia set of G, right? And so this pairing will be small precisely when most of the Julia set of G takes a small escape rate value for F, i.e. most of the Julia set of G is close to the Julia set of F, and vice versa. Okay? Does that help clarify? Yeah. This is roughly the local contribution to the energy integral, which is to say that the energy integral, the energy is roughly speaking a sum over places, properly normalized, of the v-adic versions of these things. And so that statement.
Oh, then you could say that the parameters are close to each other.
That's right. So when the energy is small, so this thing is always non-negative if you properly normalize it, and meaning choose a non-negative choice of your escape rate function here. And so if these contributions are always non-negative, then this energy is small if and only if every single local contribution is small, which means that every single pair of Julia sets is v-adically close together for every single v, which was the violation of the product formula. Yeah. And sorry, I couldn't give more an idea of Q2, but okay. That's right. Thanks, guys.